Alright. Who needs that handout that I gave out about solving 3 equation systems? Alright, you gotta go over there. Alright guys, last time we got a little bit in the 12th. Are there any questions from homework? And let me say one thing that might spur some questions. We're going to have a quiz on Thursday. I don't think I've announced any quizzes yet. Quiz this Thursday on chapter 10 and 11. There's really only 3 sections, right? There were 2 sections in chapter 10. 1 and 11 because I made the other one extra credit, right? Which was, let me try to remember. 11.2. So if you weren't here last time, I made 11.2 extra credit. So you can do it or not do it. Alright. So that's the first thing we'll do on Thursday, is that. And then spring break. Yay! Oh my God, I'm so ready for spring break. I'm sure you feel the same way. I'm so desperately ready, yes.
So, what all happened at the convention?
There was celebration. There was devastating loss, financial loss. I lost 80 cents. I'm just really bummed out. Thankfully, I'm not addicted to gambling. So I can just play a machine and go, well, I didn't do anything good. Yeah. So I think we went one time to there and we did some stuff in the hotel casino, and then we mostly just went out when we had time. We didn't skip too many workshops. The conference itself was really cool. And of course, at 9:26, I think we talked a little bit about this the other day, right? About Saturday being Super Pi Day. So, and this was a math conference, so there was a critical mass of geek that was achieved. So, on Saturday at 9:26, because those are the first that many digits of pi, right? So 9:26, we're like, oh yeah, Super Pi Day. We're all looking at each other like, okay. And then there was just another excuse to get some drinks and stuff. So hey, what the hell? We're American. We're good at that, right? Cinco de Mayo. Do you know what it is? No. Want a drink? Yeah. Go America. All right. Wait, I'm not knocking it. I had good drinks.
On page 739.
739. Mm-hmm.
125.
Oh yeah. So we really haven't gotten into section 12.2 yet. Yeah, so we're going to get into 12.2 today. We barely got into chapter 12 at all last time, if I remember correctly. So we're going to really get into it today. So anything else from 10 or 11? Have you guys tried the homework yet? It's all right to be honest. I'm not going to go just leave. You have failed. Go away. But I mean, you know what I'm going to say. It's a public service announcement. You got to do the homework to keep it fresh. I'm not somebody who does like quizzes or tests on the first day back after spring break. You have teachers that are going to do that. I never really understood that. Monday classes, they go, okay, the Monday after spring break, we're going to have a test. What sense does that make, really, in the grand scheme of things? So we're not going to do that. I'm going to give you that quiz before spring break. Because then I got like all kinds of time to grade it. Okay, so nothing else from homework? Yeah.
Number 9 on 11.1.
So what happened there? Did you run into trouble?
Yeah. When I try to combine 1 and 2. Because I did 1 and 3 first, and then I was going to do 1 and 2.
This is number 9 on section 11.1. Oh yeah, I like it. Cool. Now watch this. It's kind of nice when this happens. I think I avoided doing this last time. I didn't realize the very first problem they did this to you, but yeah. Watch what happens. What happens when you add 1 and 3?
At all. Just leaves you with y and 1.
Yeah, x is canceled. You guys see that? Negative y plus 2y is y. Z's
Cancel.
0 plus 1 is
1.
That desperately kicks ass when that happens. Right? You know what y is. So this is one of those weird things. If that ever happens, that is so desperately nice. Because what you can do now is you can go plug 1 in for y in all 3 of these. You know y is 1. You guys see that? The minute you know what a variable is, you can plug it back in wherever it is, because that's what that variable is. The whole point of systems of equations is to find the one answer that works for all 3 of these. Y is 1 is a piece of that answer. It should work in all 3 of these, therefore you're allowed to plug it in. So now I can make this first equation would be x minus 1 minus z is 0, or x minus z equals 1 if I add 1 over. Let me stop there. Do you guys see that? I know y is 1. Because when I added the first and third ones, x and z went away. Are you guys with me on that part? Yes? Okay. No, what's up? Oh, sorry.
I thought you had to add them all together at once.
No, there's nothing that says you have to. You could. I think last time we talked about the fact that you could, if it made sense. There's nothing in the world that says you have to.
You do in this case?
You totally could. I don't know. Does it do something special?
No.
Not really. But if I noticed like let's see, I don't think any of these really no. But if that would have been a negative z, you see if I add them all together then all the z's would cancel. So I get an equation with x and y in it, so I just have to kill z one more time. Remember the fundamental property of these problems, how to solve them is kill a letter twice. Right? That if you had to sum up the process we use to solve this, that's the summation. Kill a letter twice.
Why did the y equal 1 though? I mean, kill
Okay, I love it. This is nothing that I did specifically. This is I said, like he said, all right, I want to kill the x's, right? So let me kill the x's. I'll add 1 and 3. So what happens? X minus x is dead. Negative y plus 2y is y. Negative z plus z is dead. 0 plus 1 is 1. So I follow the process. And this is one little twist that I told you could happen. And when this kind of twist happens, why is it so nice? Why is that good?
You could plug it in.
Because you know what y is. It sucks when there's 2 variables left alive here, but it's better, right? You had 3 variables alive, now you want 2 alive. Anyway, sorry, I got zombies on the brain. They just caught up on Walking Dead. So these are zombies. You want to kill them. You really kill them so they don't walk around. Yes?
So I'm just trying to wrap my mind around the fact that basically you could just choose which ones to work with, right? You could just choose number 1 and number 3 equals.
Of course, you have to. That's got to be part of the process.
It's like too much free will. You know?
I understand. Because a lot of students, the further you get in math, the more you have to realize how much freedom you have.
For yourself.
Yeah, exactly.
It's creepy.
It's scary. It's sort of like moving out of your parents' house first time.
It's very uncomfortable.
Like, yeah, wait a minute, shit. Starts to sink in. Right? Of course, I remember I moved out of my parents' house. I came back to get something, and they'd already torn a wall down in my old room. I'm like, all right, so you guys are really sad.
I'm just curious as a question. I mean, involved with what we're doing, but just about you. What's the highest math that you've done? You've done physics and all that. I'm just curious.
Yes. Yeah. The highest math course I took was 896.
What's that?
That was over on the East Coast. It was, anyway, it was like higher level complex variables. And we haven't even gotten to complex numbers yet. But let's go back to this. So all I did here was, is everybody cool with this? I mean, this just happened. You have no control over this. This can happen whenever it wants to happen. When it does happen, you don't go, oh, you go, yes. Because now I know y is 1. So the first one becomes this. This is what number 1 becomes. The second one would become 2x minus 3 times 1.
So negative.
Plus 2z equals 7. So therefore 2x plus 2z, add 3 equals 10. So I get this one and I get this one. And what's really nice about those two? They only have x and z in them, right? Of course they only have x and z in them because I already know what y is. And what can I do between these two? What can I do between these two now?
Combine.
To do what? What is my purpose?
Oh, to get x or z.
To get x or z by itself, to kill one of them, right? So you can either divide this by 2, you see that? Or you can multiply this by 2, add them together, and the z's will cancel. That's your whole purpose, is to kill variables, right? Something you wanted to do ever since we introduced them to you. Here's a variable, make it die. You can actually do that now. You can make them die. Legally, right? No state will prosecute. I'm going to let you finish that up because it's your homework question. But if this happens to you in number 9, this is exactly how you proceed. And that's beautiful when that happens. Now, why didn't I plug it in the third one? I totally could. Right? In fact, if I do plug it in the third one, I'll get negative x plus 2 plus z equals 1 because y is 1. I get negative x plus z equals subtract 2. Subtract 2, Jeff. There you go. But does anybody notice how that's the same thing as the first equation? If I divide by negative 1, I get x minus z equals, that's the same thing. That happens very often. But another reason why I don't even have to plug it in the third one is I just need 2 equations that have x and z in them. So I don't even care what the third one does. I've got 2 equations with x and z, I can kill one of those. Right? All right. One person likes that. The rest of you, I don't know. Jury's out. But do you guys understand the process to use?
It's the last thing. Okay. Basically, what you do is you just plug in the y or the 1.
Yeah, the minute you know a variable, you can plug it back in.
Yeah, okay. And just anywhere you want. Just take them 2, for
You
example.
can plug it back in on all 3. Yeah. And then you just use 2 of them to kill a z or kill an x. Yeah, okay. So one way to get rid of a variable is to kill it. Another way to get rid of a variable is replace it with a number, because I figured out what it was. So the y is now gone, because I replaced it with a number, right? And now what's left is much easier equations. Okay, okay. Anything else from homework? Yeah. So what happened on that one? But did something weird happen in the process? Okay. What happened in this classroom? $21 is this dude here.
Is that 11.1?
Huh?
Is that still 11.1?
Yeah, this is 11.1, right?
Yeah.
Okay. All right, cool. So always at least double check your numbers. So tell me what you did.
Combine 1 and 2.
All right. So
Combine the second and 1, 2.
all right, cool. So your goal is to kill the x's.
Yeah.
All right. So you took 1 and you left it alone. And you took 2 and you multiply by 2, so that these would cancel. I like it. Is that cool? Just multiply this by 2. Okay? All right. So then you get 21, 8z
Equals 12.
12. Cool. Alright. And then what'd you do?
2 and 3
Alright, 2 and 3, so you had to do what with the second one?
times 3.
So you're going to leave the third one alone. And the second one, you multiply by what now?
3.
Yeah, you got to multiply by -3, right? Unless, I don't know, if you multiply by 3, you got to subtract them. And to me, subtraction is a harder property because if you're subtracting a negative, that becomes plus. So I always make sure these are opposites, right? So if you multiply by -3, you get -3x minus 18y minus 9z equals -12. Is that cool?
Yeah.
But is that what you did?
Yeah, I'm just seeing if I did it right.
Okay, good. All right. And when you add those, what do you get?
Negative 20y. Give a AZ equals what?
-12? I like it. Now, I see what the problem, right? I see. So now, if this is your fourth equation here, this is your fifth equation here. If I put the fourth equation and the fifth equation together, they're actually sort of set up to do what I want them to do, but what happens when I put them together? I get 0 equals 0. Right? Which normally means all real numbers. But be careful, what do the answers to these kind of equations look like? If you really took them all the way down to the form they should be in, what are they? The answer to a system of equations, either 2 dimensions of lines or 3 dimensions with planes, the answer is a what? Point. So, how many answers are there? When is 0 not equal to 0? Never. So this always works. There's an infinite number of solutions, right? So the answer is an infinite number of points. So this would be technically what's called a dependent system, if you were reading the book.
Yeah. I didn't know what that meant.
Dependent just means that, watch this. What happens when you add, did we add, no, watch, I really want you guys, what's 1 plus 3, don't say 4, I mean, equation 1 plus equation 3, what do you get for the x's? X. What do you get for the y's? 6y. 3z. So now watch, is number 2 really a new piece of information? If you tell me number 1, okay, I got it. And you tell me number 3, okay, I got it. And then you tell me number 2, I'm going, that ain't new. I can get that from what you told me already. That's why it's called dependent. Equation number 2 is dependent on 1 and 3. Because together 1 and 3 make equation 2. It's like this. If I said, you're twice as young as I am, you're half as old as I am. There's the correct grammar. Alright? And I'm twice as old as you are. Did I just tell you 2 pieces of information? If I said, she is half as old as I am, and I'm twice as old as she is that 2 pieces of information? No, they're dependent on each other, right? I mean, they're the same thing, aren't they? So these together are the same thing as this equation. So if they're trying to pass this equation off as new information, it ain't. You understand? So, so if I'm trying to solve a murder, I want to find all these different pieces of information so I can compare them. If I say, well, Jose said he wasn't at the bowling alley, and then I say later, Mr. Puente said he was not at the bowling alley. That's freaking Jose. You're using a different name. It's the same dude. You just told me the same thing twice. I can't figure shit out with that. I need more and more information. That's why it's called dependent. And that's why it comes out to an infinite number of answers. Because one of them actually lies on the intersection of these 2. So it's sort of like, let me see if I can make this make sense, because it's hard in the room. And this is, you guys have never seen a Rolodex. I'm almost certain, because those are kind of, you have, a few of us have, but a lot of us have never seen it. A book is probably decent. All right, you ready? All right. Here's one plane. You see this side of the book? That side of the book there? That's one plane. Is that cool? Pretend like there's only one sheet of paper. There's one plane here, right? Here's another plane here. When two planes intersect, how do they intersect? When these intersect, they create what? When the ceiling intersects with that wall, what do they create? A line. How many points are on that line? How many points are on that line? Infinitely many. Not how many do you need to draw it, but how many are on there? An infinite number of points, right? So if I have another plane, can you imagine another plane coming like this through that juncture out? Like some horrible thing has happened and something came crashing right through there? That's another plane. And where does it intersect with the other two? On that same damn line. So if the answer is where all the planes meet, they all meet at a line. So how many answers are there? Infinitely many. It's just the only way math is able to tell me that. Math says, oh shit, two of these planes, one of these planes is it meeting at the same place as the other two planes meet. They're all just meeting on a line.
I was just going to say that'd be interesting if this system would kind of teach us on physical examples like that, how this works.
Oh yeah, oh yeah.
Because this is an abstract, concrete
Concept, yeah, I understand.
It's abstract and concrete.
And to me, walls are awesome examples of planes.
Yeah.
Right? But the one where they meet a line is weird to try to find a good example of that. It's really easy for planes to not meet. What would the solution be if that was a plane and that was a plane? No solution. So what would you get here, for example, if there was no solution? 0 equals 1. Or anything that's not true. That's trying to tell you, oh shit, they don't meet. All right? These guys meet. They just meet at too many places. They don't meet at a single point. They meet at an infinite number of points. So all you got to do as an answer is just say infinite number of points. Don't say all real numbers because that doesn't make a damn bit of sense. Because answers are points here, right? So this would be infinite number of points. That's the solution, is an infinite number of points. Now there's a higher level math class where you actually analyze the geometry of the points. But we're not going to go there.
So you would stop right there?
Yeah, that's plenty,
Oh, okay.
right? In the book, we call it a dependent system of equations. We've seen that word before. Inconsistent equations would be ones that have no solution, right? We say they're inconsistent with each other because they don't agree. They don't meet somewhere. Okay, maybe. It might just be the way some of you guys just look, but you always look so desperately worried.
So
Yes?
if it would have been like 1 equals 1, it's the same thing, infinite number of points.
Yeah, anything true here, but what normally happens on these is you'll get 0 equals 0.
Okay.
Yeah. Because everything will end up canceling it down. But anything that's always true tells you that you have an infinite number of solutions. Yeah.
So these planes are like, if you're working in a program that does like 3D modeling, it would be like you have your X, Y, and Z plane.
Look at you, yes. So if you've done any of that stuff, now you can see. So we normally work, when we graph things, we work in what's officially called the XY plane. It's a plane, right? If I could put a point anywhere, theoretically, I can, climb a line or go to the top of the point. It's still on the same plane, right? How far does this go? It goes forever. That's the point. And then if you add a third variable, if I could draw a line out here, right? Oh shit! And now I can locate a point in 3 space. Now I can have an x. I can have an XZ plane, which would be this plane here. This would be the XZ plane, like this. Or the ZY plane would be like this. Oh, scheiße. So the XY plane, the XZ plane, and the YZ plane, they all meet there. Right? And they have pictures of that in your book, where 3 planes meet perfectly. Bless you. Okay, cool. And again, I'm trying to show you what this is geometrically, but I'm also trying not to go too far down that road because the curriculum of this course doesn't require us to fully understand all the geometry involved, but it does help understand what the hell's going on.
Yeah, but if they taught us that first, then it would retain better and it would be more purposeful.
And they have, my pictures and my stuff can only do so much, but like on page 678, they have some really good images, and page 676 of what could happen with your
The
planes.
curriculum is still so deprived of these things, no matter how many pictures you post.
I remember earlier you were saying it's all useless, and now you want more of it.
Me? I never
Yeah.
said it's all useless. He said it's all useless. Where is it?
Oh, he's not. Is he here?
No, he's not here.
Oh, he's not here. Sorry.
I think you said it was kind of useful. Well, you said it was like a language.
I took that back.
Oh yeah, you did. You're okay.
But no, it was just.
It was somebody else.
Yeah, it wasn't him. He never said
That's
it's all
my bad.
useless.
I didn't mean to bring it back up because I know you took it back.
I never said it's all useless.
All right, my bad. It's just that it's funny. I always get two extremes. It's like not enough or too much. I'm like, shit. So we try to land somewhere in the middle.
No, I said it's a way to see things from different angles. It
Exactly.
trains you to see the world.
I like it.
You do one more? Because
One more.
I'm having trouble with the one that you don't have a variable. Either you don't have y or you don't have z.
Oh, like they have a hole there?
Like 33? Yeah.
All right, let's see. All right, so real quick, and then we got to get to some new stuff. There are some problems where variables are already missing. Now 33 is kind of funny, and I want to show you what's cool about 33 specifically, so I'm not going to take this too far. I mean, the way they wrote 33, they're almost telling you what to do. Don't feel bad if you don't hear them, but I want you to realize, and actually this is more, it's not even the right form, like the x is on the wrong side and stuff, right? But they actually did that on purpose to help you see what you should do. Y is 2x plus 3, right? Okay, that's a weird way to say that. Z is 40 plus x.
I got it now.
Right?
That is.
So then you say x plus y. Well, what's a better thing to put there?
That.
Yeah, so this is set up for substitution. So they're trying to show you, even with systems of three equations, it's not always elimination. Sometimes substitution helps. But you actually have to have this specific situation. You have to have a letter already, or two letters solved in terms of one of them. That has to already be there. It's not a situation that we run into a lot. But if it does, that's awesome. So you would just put this, that is y, so you put it there. And that is z, so you put it there. And then you have x plus x stuff plus more x stuff equals 83. You can solve for x. And the minute you have x, you have y and you have z, because they both depend on x, right? That kicks so much ass. Okay. Good. All right. So we're going to get back into chapter 12. Okay, good. I said that. Just to get us back into what's going on here, two things. All right, let's try that. What would that be? So, what are you asking yourself? What does a fourth root ask you? What's the question that a fourth root involves? Fourth root is 16. What do you have to think about?
What number? What number can 4 times?
Beautiful. What number does it take 4 of to multiply to be 16? 2. So it takes 4 2s. So the fourth root of 16 is 2, because if you break 16 down, you get 4 2s. So the fourth root just takes one of those. Whereas if I start, now I really want you to get this. If I start with 1 2, I got 1 2 up there, don't I? And if I put a fourth power on it, now I have 4 2s. Whereas a fourth root says, oh, you got 4 2s? Well, I'm going to take it back down to 1 2. So they just undo each other. A fourth root is the opposite of a fourth power. It says, oh, if you got a 16 inside, then that must have come from a 2 4 times. That's why that's the answer. Now what about here? Why is this one nice? You guys remember how to do this? Break this up into 4 parts. What's your brain, what's your gut telling you that's going to be?
X squared.
X squared. So your gut's right. Because if you break x to the 8th up into 4 parts, isn't it going to be x squared, x squared, x squared, x squared? So watch the shortcut here. 4 goes into 8 twice. Right? That kicks so much ass, and it actually works forever. So what's the 7th root of a to the 63rd power?
A to the 9?
Yes, because 7 goes into 63 9 times. Right? That can't be right, Jeff, man. That's stupid. But if you think about it, of course that's the way it is. If you multiply 8 to the 9th, if you raise that to the 7th power, let me say it like that. What do you do with the powers?
You multiply.
So if this is supposed to be the opposite function of raising to a power, here you multiply, here you have to get back to where you would have been, right? If they're opposite functions. So a radical is the opposite of a power. All right. Can't tell with you guys. I don't know if some of you are like, I know all this shit, and the rest of you are like, I don't know any of this shit. All right. I'll just keep it a secret. It's not a good idea. Oh, let's do this. Let's talk about domain for a second. Let's get variables out of the way for a second, or just one variable will come in there. What would the domain be for this? I mean,
X.
what can't be true about x?
Negative, right?
Can't be negative. Good. So what's the opposite of negative? It's got to be not negative.
All positive.
So x, the inside's got to be positive. What else could be? Not just positive, it could also be 0. Because what's the square root of 0? 0. 0 times 0 is 0. It's crazy. Right? So the domain for this would be x greater than or equal to 0. Or you can write that, of course, as from 0 to infinity. It's a good place to start. Because, of course, if I try to plug a negative number in there, I get a non-real number. Right? I can't take the square root of negative 4 and get a real answer. I got to say it that way because some of you guys know complex numbers. Right? Most of you guys probably must have seen complex numbers sometime. So what about, how do I do something more complicated like the domain of this? Whenever I ask you a domain question, try to say in English what the restriction is. So here we said the inside had to be at least 0. That restriction is always true because that's the fundamental property of radicals, of square roots. Let's be careful. Because that's what we're looking at here, square roots. So the inside, so if I say it in English it would be inside is at least 0. Or if I really want to say full English, the inside, there you go, Jeff. All right? Not Tarzan math. Inside greater 0. Now replace this with the math. What is the inside? What's the inside? 7 minus 3x. Is at least. How do I write that in mathish? Let's do it again. Greater than or equal to 0. There you go. And how do you get the domain then? You solve that. Because don't forget, how did we get the domain of something like this here? We said the bottom can't be 0. So we said it in English, and then we wrote it, the bottom is x squared minus 9, can't be 0, and then we solved it. Factor it, get the two numbers, right? That's awesome. Domain always works that way. If you can say in English what the restriction is, then write in mathish what that is, and then you solve it. And you're done. It almost seems too easy to trust. So how do you solve this? Subtract 7.
Divide by negative.
Good. Flip the sign because I divided by a negative. 7/3, kick ass. All right, so that's the domain. You can graph it in interval notation, whatever I ask for. But that's fundamentally, that's the domain of this. If I try to plug in something greater than 7/3, this thing will freak the hell out. How are we doing there? Is that decent? So, with all that said, what about the domain of this here? What's different? It's a cube root. Is there anything different about cube roots versus square roots? Yes. For example, recall. What's the cube root of -8? -2. Because what's -2 times itself 3 times? -2 times -2 is 2. It is 4. There you go, Jeff. Times another -2 is -8. So odd roots are more laid back. They're like, okay, cool. You want to be negative? That's cool. Even roots, you're negative? Shit. Right? They freak out. So the funny thing is, since odd roots can handle negative and positive inputs, this domain is all real numbers done. So if I had a 5th root or a 7th root, any odd root, it can handle negatives inside. Because an odd number of negatives would multiply to still be negative. Whereas an even number of negatives, what would happen? They would pair up, and the negatives would cancel. Right? So that's why the 4th root of -16 can't work. I can't multiply something by itself 4 times and get -16. If it's positive, it's positive. If it's negative, the negatives cancel, it's positive. Oh shit. Right? Okay, maybe. Alright. Cool. So there are some domain questions in there. And somebody might realize that if I'm talking about domain, we'll probably immediately follow that up with graphic. So how would you graph this? What do you do when you have a function that you're not sure what it looks like? What do you make for yourself to graph? Yes, good. I was about to say I failed you miserably. I don't know if you guys are just shy. Or if you really don't know. If you really don't know, that's a problem. But you can always make a table if you're not sure what something looks like, right? Always. And now we know, we said earlier, what was the domain of this guy again? What was the lowest number I can put in there? 0. So that, knowing the domain helps me figure out how to make my table. When I make my table, I'm not going to put -1 here or something. So I got to start at 0. It's the lowest I can go. Square root can't handle stuff below that. So 0 is a smart number to put in there. What's the square root of 0? That's great. What's the next good number? 1 is good. Square root of 1. Oh my God, this is a very weird function. Would 2 be smart? What's the square root of 2? 1.415. It's nothing nice, right? What's the next smart number?
4.
The next square. Makes sense. What's the square root of 4? 2. What's the square root of 9?
3.
All right, that's plenty. Right? Just need a few points to get the shape of this thing. So if I go to start to plot points, let's see if I can go out to 9. Almost. So let's see, 0, 0, 1, 1. So start to look at it. It's not a straight line. 4, 2. So 1, 2, 3, 4, 2. 9 goes to 3. 1, 2, 3, 4, 5, 6, 7, 8. 9 goes to 3. So this thing looks like, whoo, make that big and you're fine. What does it look like it's missing on this side to be something we know the shape of? Yeah, it's missing like this piece to it, right? And it's missing this piece because this guy can't go negative. So it's like a parabola that went, or whatever sound effects happen. God, his reaction. I saw it. I saw the reaction. Shit. Yeah. All right. So you guys really are here, not just a figment of my imagination. Yes?
Do you have a handout for this?
For this? No. No, because I figure there's enough in the book. I do have a handout for something coming up that I don't think there's enough of in the book. Yeah. But they go over how to graph this in the book, just like this. Now, what do you think is going to be different about like a cube root? What was I not able to plug into here? And how does that show up on the graph? I couldn't put any negative x's in, so that's why back here the function is nowhere. So you guys take a minute. Let me give you some stuff to plot here. Graph g of x equal the cube root of x. Let me help you out a little bit. Shouldn't be too evil. Quickly see how this looks. So I'm going to go out to 8. So what's the cube root of negative 8? Negative 2. Good. So that's how it comes out negative at the end. That one odd extra negative. 2 negatives die. The third one's still there. Ha ha. Cube root of negative 1. Negative 1. Cube root of 0. It's crazy. Cube root of 1. Cube root of 8. Sweet. So then you get 0, 0. 1 goes to 1. Negative 1 goes to negative 1. 8 goes to 2. And negative 8 goes to negative 2. So then you get this neat. So what's that look like fell over? So a square root looks like a parabola fell over and lost the bottom half. This looks like what fell over? So x squared stuff looks like what? The x squared looks like parabola. Right? And it actually would touch it. What does an x cubed look like? You guys not know? Okay, all right. What's negative 2 cubed? What's negative 2 cubed? Yeah, what's negative 2 times negative 2 times negative 2? It's not cube root. I agree with you that if I asked you that question, you're allowed to go, I have no idea. But negative 2 cubed is just negative 8. Blah, blah, blah. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. It looks like that. That's what any odd power would look like. X to the 5th would look like that. X to the 7th would look like that. X to the 10th would look like this. Any even power. So if you have this fall over, it looks like this. If you have this guy like twist and fall over, it looks like that. And why does it make sense? Because a cube root is the opposite of a cube. So graphically, you should be able to kind of see the idea of opposite up there. They are opposites of each other. All right. Okay. So there's a little section in that first. This is still section 12.1, where they want you to graph a few things. You just got to make a little table of values and graph it, just like we did. Section 12.2. This is where things get kind of interesting, and this is, like we're so used to the square root symbol, but it didn't have to be that way. Somebody came up with that symbol and then told everybody else what it meant, and then everybody else went, okay. And the one guy that said, I don't like that, they shut up. It was a different time, right? I don't know if you guys ever realized that that's true. I mean, that symbol was not handed down to us by aliens that said, we'll blow you up if you ever use something else. It was something that humans came up with. The square root symbol could have been a box with a dot underneath or something. It's just that that guy wasn't there that day, so they voted on something else. Right, the box dot dude, right, wasn't there. Anyway, so we're going to see that there's a different way to write the square root that actually makes a little more sense. So here we go. What does the square root do to something fundamentally? What's the square root of 9? 3. Good. I've somehow scared you, and I'm sorry. You guys don't even want to answer anything. Square root of 9 is definitely 3. Why? Beautiful. So one way to answer that is perfect. Nothing wrong with that answer. 3 times 3 is 9. But also think about it this way. Isn't 3 half of 9 multiplicatively? Let me say that again. If you cut 9 in half, sort of like you're factoring a difference of squares. Remember what I said about this? You cut everything in half? Nobody thought I was insane when I didn't write it at 4.5. Because half of 9 additively is 4.5. Is that cool? But half of 9 multiplicatively is 3 and 3. All right. I like it. And then, of course, minus blah, blah, blah. So that's why square root of 9 is 3. And so what I'm doing is a exponent deals with what operation? What does that 2 really mean? I know it means squared, but what does that really mean fundamentally? How do I do that? Multiply. Good. So exponents deal with multiplication. So now watch this. If a root is cutting something in half multiplicatively, that's the opposite of doubling something multiplicatively, right? Let me say that again. A root is cutting something in half multiplicatively. That's the opposite. If I said double this multiplicatively, you do 3 times 3, which is 3 squared. So watch what happens. It sounds like it's going to be really hard, but it isn't. Just trying to figure out how to explain this really well. Square root of 9 is the same thing as 9 to the 1/2 power. Because a power is all about multiplication, and we already have verified with everybody that you all agree with me that it makes sense to say this is cutting 9 in half multiplicatively. Now really, to make you guys really believe me, how do I write 9, 3 to the 2nd? And that's 1/2 is still there. Is that cool? So I just rewrote 9 as 3 squared. And what do you do with these powers? In this situation, when you raise something with a power to a power, what do you do with the powers? Multiply. What is 2 times 1/2? 1. What's the square root of 9? 3. I'm not saying that we're suddenly going to do this shit. This is me explaining to you why it makes sense that we can write roots as fractional powers. Right? I still want you just to do square root of 9 equals 3. Don't do all this weird shit. All right. But now this is interesting, because actually we didn't really need the square root symbol. We could have just put 1/2 up here. So what do you think a cube root is? Cube root of x equals x to the 1/3. That's insane. That's awesome. Because what does a cube root do to something? Cuts it into thirds. That's exactly what this guy says. Cut that into 1/3. You guys with me so far? Some things are easier to do if they're written as powers, and some things are easier to do if they're written as roots, just because we're used to roots more than we are with powers. So let me show you an example of something that's easier to do if it's written as powers. Oh, well, let's see. Well, actually, that's getting a little ahead of myself. I don't want to go there quite yet. But let me show you a couple things here. So just to make sure you can go the other way. What would x to the 1/7 be? If x to the 1/2 is the square root of x, x to the 1/3 is the third root of x, x to the 1/7 is the 7th root of x, because it would cut it into 7 parts, right? So that's the 7th root of x. So what would x to the 2/7 be? Uh-oh. Oh, scheisse.
7 and then x.
Beautiful, because that's the root What's beautiful is where are roots on most plants? In case there's a botanist out there, where are roots on most plants? On the bottom. So the bottom is the root, the top is the power. Kick ass. So if you can rewrite from exponential to radical, that's one skill you got to have. So I can write this as the 7th root of x squared. Let me see if you guys are cool with this. That's the same thing as the 7th root of x squared. Those are the same thing. Why the hell is that, Jeff? Just tell me this. Screw you, math, dude. So because, let me see if you guys are cool with this. Isn't that the same thing as that? Is it? Why? What would you do with these? And what's 2 times 1/7? 2/7. And do you see how that's the same thing as this one, right? The x squared is inside of a 7th root. Is that cool? But couldn't I have written it like this? Those are still 2/7 when you multiply them, right? And look, the 7th root is inside of a square. Holy shit. So it doesn't matter where you put that power. And why is that good to know, Jeff? Why? What trivia is that? You play Jeopardy and I can get one more answer right? No. I feel like I'm selling something. I sort of am, I guess. Big slices. It
That's
does.
called radical? Is that what you said? Like what you're doing right now, like how you're switching it? Is that called,
Well, no. This symbol is a radical. That symbol is the radical. Yeah. Well, I get, in a way, what we're doing is radical, but the symbol is a radical, right? And then the other one is just realizing that radicals really are just one way to represent rational powers, fractional powers, right? Yes, sir.
So what you're doing right now is just showing us like the reason it is the way it is. So we're not going to need to actually learn this or write it this way at all, right?
You have to understand this, and you have to be able to rewrite from one form to the other.
yeah, like how would you ask this? Like,
Well, it's in the book, actually. It'll ask you, let's see exactly how the book
how
asks
will you
you.
know when to...
Here we go. It would say, write an equivalent expression. If they gave you this, it would say, write an equivalent expression that uses powers,
Okay.
or uses exponents, right? So it's telling you, don't write a radical, write exponent. Or it would say, write an equivalent expression using radical notation, right? So they just want you to take it from powers to radicals, or from radicals to powers. So here's an immediate kind of useful tool for this. 16 to the 3/4 power. That's not easy in that notation because I'm not used to that notation. But how do I change that into radical notation? Yeah, the root on the bottom, 4th root of
16.
Now where do you want to put the 3? Because do you know what the 4th root of 16 is?
No.
You sure?
Oh, yeah.
Think about it. Yeah, it's 2. So do you want to put the 3 in there and now do the 4th root of 16 times 16 times 16? Hell no. I want to put the 3 out there. So thank God I can. Thank God it's allowed. Because what's the 4th root of 16? 2. What's 2 cubed? Because it's still got a cube there, right? 8. So 16 to the 3/4 power is 8. Now let me blow some of your minds real quick. And if you don't like this, never do it. It's not necessary. But this is kind of cool. Break 16 into 4 parts for me. What would it be? 2 times 2 times 2 times 2. Take 3 of those 4 parts. What do you get when you multiply those? 3/4 of 16 multiplicatively is 8. Because 16 has 4 2's, you take 3 of them. It's 8. I know, it's cool. You never have to do it that way. It's kind of nice to see that that's what's going on. So it kind of is closure. Because 16 to the 1st power is a full 16. So 16 to the 3/4 power should be a little less. And it is. Sweet. And that's why. You don't give it the full power. You give it 3/4 of the power. Shit. Right? All right. Maybe. Not too bad. So here, you guys try this one. So what's the root going to be?
3.
Third root. Where are you going to put the 4?
Outside.
Outside always, because the key root of 27 fourth power sucks. But key root of 27 is 3, because it takes 3 3s to make 27 multiplicatively, right? And so that's 3, so you still have a fourth power. And what's 3 to the fourth power? 81. And why does that make sense? Because 27 to the 3/3 is a full 27. 27 to the 4/3 should be more. Somehow 4/3 is big. But multiplicatively, that's why it grows even bigger, quicker. Stronger, faster. All right. So what would okay, cool. Let's do this. Oh, I've offended people. What would happen? Let's do an easy one first. Okay, this is very, very, very simple. Just to make you all tense.
X to the 12.
It's crazy, right? So when you multiply, you add powers. We all know that. Does that property say anything about what the powers have to be? When you multiply like bases, you add the powers. That's the end of that property, right? So for example, just to go beyond what we have to do, what would x to the m times x to the 2m? Don't make more of it than it is. Yeah, when you multiply like bases, you add the powers. That's x to the 3m. Right? So does math give the first shit what's up there in the exponents? No, the property doesn't care. The properties never care what's in there. Right? So now that we know that there are such things as fractional powers, you're going to see problems like y to the 2/7 times y to the 1/5. And the thing that suddenly people are going to forget is how fractions work. They're going to tell me the answer is y to the 3/12. Do you see where that would come from? What did somebody do to get 3/12?
Add it.
Holy shit. And then a little tear comes out. So, properties never care what's in them. Fractions always require LCD when you want to add them. Always. They don't care where they came from. So the property says, add these together. That's what the property says. And of course the fractions say, you can't add this again until we have the same denominator. Right? So be careful. Don't suddenly think the fractions suddenly can add differently. No, they have to always add the same way. So the LCD here would be 35. So you got to give him 5 and him 7. Give each other what they are. Oh, that's nice. So you get 10 plus 7, 17 over 35. Bam. Right? Bam. I like it. And all the other properties are still there. So if I was dividing these, you would have to subtract the fractions, right? If I was raising 2x squared y to the 3/4 to the 1/2 power. That's gross, Jeff. Oh, well, too bad. Make that a 4. I might as well make it nice, right?
2 outside.
2x.
Yeah, so you distribute the power, right? So 4 to the 1/2 power. I'll just write that for a second. X squared to the 1/2. What do you do with the powers? So what's 2 times a half? 1. And then here the same idea, right? Y to the... What do you do with the powers?
Multiply.
Multiply. So 3 times 1?
3.
4 times 2? 8. And what's 4 to the 1/2?
2.
It's good. Somebody was trying to tell me that earlier. So when you raise things with powers to a power, you multiply the powers.
But you can multiply straight across on those?
I'm sorry?
On 3/4 and 1/2, you can just multiply straight across?
You have to. I mean, that's... How do you multiply fractions? Now, if you're thinking cross multiply...
I forgot about that. Yeah, I mixed it up with that.
Strike that out of your brain. That would be if these were equal to each other, like with the next summer. Then you can cross multiply, right? But it's just straight up multiply. Multiply. 3 over 8.
You would still be able to cross multiply, right?
The only time that you can directly cross multiply two things is if it's a fraction equals a fraction. That is the only time you're allowed to cross multiply. The minute students learn cross multiplication, they try to do it everywhere. Just say to yourself, am I in the specific situation where cross multiplication works? No, I don't have fraction equals fraction, right?
Even if it what?
No, you're thinking cross reduce.
Oh, yeah.
Okay, good. All right. Now I understand what you're saying.
Oh, never mind.
So totally you could do that. In fact, we did that here. 2 times a half, we cross reduced. And that's why it came out to be 1. I like it. Good. There's nothing new there. All the properties of exponents have got to be the same because they don't care if there's fractions or letters. They don't care. They're the same. Okay. All right, there. So, what do you think about this here? That's a little backwards from what we used to, right? But the book kind of gives you a hint. The book would say, use rational exponents to simplify. I might not be that nice. But what would it look like if you wrote it with a fractional power? Yeah, good. Power is 3, the root is 6, and then we'll catch up. That reduces to 1/2. And if you wanted to write it back in radical form, what would it look like? Square root of a. Kick ass. So the 6th root of 3 reduces to the square, 6th root of a cubed, reduces to the square root of a. Do you guys see that? So that's just that fundamental skill of rewriting radical notation into exponential notation, because then it's just a fraction, and then it reduces. So why does it make sense? We've done this since day 1 with radicals. I asked you what's the square root of x to the 4th. In fact, we did that earlier today. And of course, what is the square root of x to the 4th?
X to the 1/4? No, I mean to the 4.
Shit. Now you guys are mixing it. We knew this before I thought about any of this. It's x squared, right?
Sorry.
Right? Because you cut that in half, it's x squared. But now if you do apply this, what's understood to be here? 2. So this would be x to the 4 over 2, which is x squared, right? That's why that works. That little shortcut works. Okay.
Also, that's always 2.
Yeah, if there's nothing there, it's known to be a 2. Yeah, there are several things. In fact, remember, we know already there's a 1, there's a 1, there's a 1 there. Good Lord. Right? So this is an understood 2. We just don't want to save time writing. Like, we're really lazy.
Why does that cut in half with 3 over 6?
Oh no, what is 3/6? Reduce 3 over 6. Yeah. The minute you write it in fractional exponent notation, it is a fraction. You can do whatever you can do with fractions to it. That is a fraction. It's on the A. It's like up there, but it's still the fraction 3 over 6.
I see.
Cool. Okay. And then finally, this is the last topic for today. And then I got my little handout. I'll give to you. I'll probably have to do it next time after the quiz, but let me see if you guys can understand this. This is section 12.3. Multiplying radicals. So we're going to talk about multiplying radicals. Incredibly enough, we're going to follow that with the discussion of dividing radicals. And then we'll talk about adding and subtraction radicals. It's crazy. And then we'll talk about radicals inside of equations. Oh, baby. Right, it's always kind of that progression when we learn a new function. So let's try to figure out what's going on here. So if I had the square root of 2 times the square root of 3, what do you hope to God that is? Please, math, let that be square root of 6. And thankfully, math goes, I will allow it this one time. It says, I'll let the easy answer be the right answer. Now let's investigate why that's the right answer and what to be careful about. This was easy because the roots are the same. If they're not the same, you're screwed, but we'll figure out a way around it here in a minute. How do I write this with a fractional power again? 2 to the 1/2. 1/2, because that's an understood 2 there, right? So first power, a second root. So it's a 1/2, and that would be 3 to the
1/3.
1. What's the root?
1/2.
Yeah, there's still a 2 there, right? Nothing there, so it's a known 2. Now, I'm going to take the 1/2 out. Because if I had 2 times 3 to the 1/2, I could distribute it to both. So math goes both ways always, right? Don't judge it. So I can take the 1/2 back out there. Is that cool? You guys see that? Because wouldn't that just become 2 to the 1/2, 3 to the 1/2, right? Is that? I'm overanalyzing this very simple thing, but you have to understand why it works. And whenever it's easy, you got to go, all right, but why does that work? Because the easy stuff normally doesn't work.
This is like grammar for
Pretty much. So that's going to be 6 to the 1/2, which is
6.
yeah. So never ever do that, right? That's just why it works. Now you just do it because it works. So what's got to be true about the roots, though? Of course, they have to be the same, or else I could never have done that step, right? They were the same. That's why I could take them out. So what about the cube root of 7 times the cube root of 11?
There's a cube root of 77.
Yeah, it's awesome. It's beautiful, right? So it's the cube root of 77. And then, of course, you know I'm going to be evil sometimes.
But square root of 7 times the cube root.
Yeah, exactly. And actually, the evilness becomes easy if you let it. So if I said the cube root of 7 times the square root of 11, and I said simplify, you would say, it's already simplified.
Yeah.
What do you want? Because that's a cube root, that's a square root, can't go together. But watch this, and especially bad because that's a 7 and that's an 11. There's just nothing the same about them. But watch, this is kind of nice. Watch this. What if I had the cube root of x times the square root of x? Now this is what I wanted to do earlier, but it was a little too early. Radical notation sucks here, but what other notation do we have available? What other notation can I use? Not radical notation, but exponential notation, right? So what would cube root of x look like? X to 1/3. You just had ESP earlier, and you knew it was coming. And what does the square root of x look like?
1/2.
And now math takes over and says, oh yeah, I can do that as long as I get... What do you have to get before you can do this? What do you want to do with the powers? You want to add them, so you need common denominator, right? Now what? Now, you guys see that? Because what the property of math says, when you multiply like bases, you add the powers. This is really cool if you let it be. I say that a lot, but I won't. What is the LCD?
6.
So that'll be x to the 2, 6, right? Plus 3, 6. Now watch. What's on the bottom? Why was that a 3 on the bottom? Because it was a third root, right? And why couldn't I multiply these? Because the roots were not the same. Finding an LCD makes the roots, because now they would both be a 6th root. So do you see how it all comes back together? So mathematically, I can't multiply these because they're not the same root. So just because I change that, why would that change? Because this allows me to get both the roots to be the same. So you can never go against that rule. You can't multiply them, they're not the same roots. I'm not going against that rule. LCD makes them the same root. It's kind of neat. So you get x to the 5, 6. Or as a radical, what would that be? And I put it on the inside because who cares? It's x. I can't do anything with it anyway. And a little teaser. Oh, man.
So,
Yes, ma'am.
That one, so the restriction, that's the simple, yeah.
Yep, so you would just circle that. You'd say already simplified. So a little teaser, and then I'm going to give you this handout. Bear with me, almost there. And don't leave because you want this handout. What's the square root of 25? 5. What's the square root of 50?
No.
It's not cutting 50 in half, right? We already have a function that does that. It's called divide by 2.
7 point something.
Yeah, it's like 7 something, right? But here's the cool thing. Isn't 50 25 times 2? And if these are, how did I get here? If math can put radicals together, I should be able to tear them back apart. So wouldn't this be square root of 25 times square root of 2? Isn't that where that... What's the square root of 25? 5. What's the square root of 2? I don't know. So it stays. This is called, what I call reducing the radical, because it almost feels like reducing a fraction in a way. You do the part you can, you leave the part you can't. But the book and everybody else calls it simplifying radicals. So that's what I titled this little handout. If you want to, you can look at this. But next time we'll go fully over this.
So the ones that can simplify.
Yeah.
At the end, because
Just
you can't simplify the radical not. They'll just be whatever number it is. Grab. Oh my God. Are a lot of people drop, or am I just missing a lot of people to early spring breaks?
Can I check 11?
Yeah.